Introduction to regex in Python. Regular expressions, or regex, are special sequences used to find, match, and replace patterns in text. Regex helps you search for words, symbols, or patterns in big texts easily and quickly. It is used in web scraping, data cleaning, form validation, log file analysis, and more. In Python, you can use the built-in area module to work with regular expressions. Running the cell now. Import the warnings module and silence warnings. Now import the regex module. It is built-in, so you do not need to install it on Windows. Running the cell now. This code sets up the environment for using regular expressions in Python by importing the rea module and suppressing warnings for a cleaner output. Although it produces no visible output, it is essential groundwork for applying regex functions in the upcoming lessons, ensuring that you can confidently build and run regex patterns without interruption. Core regex concepts in Python. The rea module has functions like search, match, find all, sub, and compile. A pattern is a string that tells what you want to find. You can use special symbols. $*+, \. Flags are used to control how regex works, like re-ignore-a-case. Match objects tell you about the results. Running the cell now. Find the words in a simple text. Here is the test string. Find all exact matches for hellos using re-find-all. Print the matches that are found. Running the cell now. This output shows that re-find-all, hello, text, found only one exact match of the lowercase word hello in the text. Notice it did not match the capitalized hello because the pattern is case-sensitive by default. This highlights the importance of understanding case sensitivity and when to use flags like re-ignore-a-case in regex. Now match hello without caring about uppercase or lowercase. Find all matches for hellos using re-ignore-a-case. Print the matches. Now it finds both hello and a hello. Running the cell now. This output shows that re-find-all successfully matched both hellos and a hello in the text, demonstrating how the re-ignore-a-case flag makes the search case-insensitive. Notice that without the flag, only exact case matches would be returned, so this code is key for finding patterns regardless of capitalization. Check if the text starts with a hello. Use rematch to do this. Print if a match was found at the start of the string. Running the cell now. The output true confirms that the text begins with hello, demonstrating how rematch checks for a pattern anchored at the start of a string. This highlights the key difference from research, which scans the entire text, emphasizing how match is useful for validating prefixes quickly. Now search for the word Python anywhere in the text. Use research to look for it. If found, print the place where it starts. Print not found if the word is not in the text. Running the cell now. This output shows that the word Python was found starting at index 22 in the text. This confirms that research scans the entire string and returns the first match's position, demonstrating how regex can locate patterns anywhere, not just at the beginning. Notice this behavior helps when you want to find if a pattern exists, regardless of its location. Beginner regex examples. Strings can be fully or partially matched. Numbers like \DA match any digit, \WA matches letters or numbers, and a \S matches spaces. Quantifiers like asterisk, plus, and tell how many times to match. Running the cell now. Find all digits in the sample text. The test string contains numbers. Use a \D to match each digit. Print the list of digits found. Running the cell now. This output shows all individual digits found in the string using the pattern \D, which matches any single digit. Notice how each digit is returned as a separate element in the list, demonstrating that find all extracts every match rather than the whole number. This highlights how simple digit matching works in regex and sets up understanding for combining quantifiers to match multi-digit numbers. Now find all whole words in the sample text. Use \W+ to match parts with letters and numbers. Print the list of words found. Running the cell now. This output shows a list of all words extracted from the sample string, matching sequences of letters and digits using the pattern \W+. Notice how a user 123 and 67 are included as full tokens because \W matches both letters and numbers, illustrating partial matches for mixed strings. This demonstrates how quantifiers like plus capture entire words, not just single characters. Find all spaces in the sample text. Use \s to match any space character. Print the number of spaces found. Running the cell now. This output shows that the regex pattern \s successfully found 3 space characters in the sample string. Notice how \s targets any white space, and the count confirms how many spaces appear, demonstrating partial matching of specific character types. This connects to the lesson by illustrating how simple patterns can quantify occurrences of spaces within text. Replace all digits in the sample text with stars. Use resub to do this replacement. Print the changed text. Running the cell now. This output shows how the resub function replaces every digit \d in the string with an asterisk. Notice that all numeric characters, regardless of where they appear, are masked while the rest of the text remains unchanged. This demonstrates how regex patterns can selectively transform parts of a string using simple substitutions. Split the sample text wherever there is one or more spaces. Use resplit to do it. Print the list after splitting. Running the cell now. The output shows the text split into separate words using the regex pattern \s+, which matches one or more spaces. Notice how each word or number becomes an individual element in the list, demonstrating partial matching and how \s can be used to split text by spaces. This illustrates the intent of using regex to break a string into meaningful parts based on white space. Intermediate regex examples. Use groups to capture parts of text. Patterns in brackets match any character inside. Use $caret to match the start and $, to match the end of text. Running the cell now. Use capture groups in regex to get parts of an email address. The email string has some text with an email inside. Search for the email pattern using groups. If matched, print the username found. Print the domain part found. Running the cell now. This output demonstrates how capturing groups in regex extract specific parts of a matched string, in this case, separating the username and domain from an email address. Notice how group 1 captures the text before the @ and group 2 captures the domain after it, illustrating how parentheses can isolate meaningful subpatterns within a larger match. This technique is essential for parsing complex text by focusing on relevant segments. Match phone numbers in 2 possible formats. The phone string has 2 numbers. Use regex to find both patterns. Print the numbers found. Running the cell now. This output shows that the regex successfully matched 2 phone numbers with different separators, either hyphens or spaces, as intended. Notice how the pattern \d3, \d3, \d4 captures numbers with a digit group followed by either a hyphen or space, demonstrating the use of brackets to match multiple possible characters. This reinforces how to create flexible patterns that adapt to slight variations in the text format. Find all vowels in a sentence. The test sentence has some vowels. Use brackets to match any vowel. Print all vowels found. Running the cell now. This output shows all the vowels extracted from the sentence using the pattern a-i-o-u, which matches any vowel character in the text. Notice how the list contains each vowel found, preserving their order but ignoring case due to re-ignore a case. This demonstrates how brackets allow us to capture a specific set of characters from a string efficiently. See if the sentence ends with an exclamation mark. Use the dollar symbol to match only at the end. Print if there is a match. Running the cell now. This output shows that the regex pattern dollar successfully matched an exclamation mark at the end of the sentence, confirming the sentence ends with exclamation point. Notice how the dollar anchor is key here. It ensures the match is only true if the exclamation point is at the very end, demonstrating how to precisely target text boundaries using regex. Compile a pattern once to use it many times. Use a \d+ to match one or more digits. Find numbers in a new string using the pattern. Print the list of numbers. Running the cell now. This output shows the numbers extracted from the string using the compiled regex pattern \d+, which matches one or more digits. Notice how findAll returns all instances as separate strings, demonstrating how grouping with quantifiers helps capture each number individually. This reinforces the lesson's focus on using regex patterns to isolate specific text parts efficiently. Advanced regex examples. Lookahead and lookbehind let you match text only when it is before or after something else. Non-capturing groups help group patterns without saving the result. Running the cell now. Use a positive lookahead to find numbers before kilogram. The weight string has numbers with kilogram or pound. Match digits only if they come just before kilogram. Print the list of numbers found. Running the cell now. This output shows the numbers that appear immediately before the unit kilogram in the string, demonstrating a positive lookahead in regex. Notice how only 55 and 70 are matched, excluding 123 since it's followed by pound, highlighting how lookaheads let you assert context without including it in the result. This confirms the lesson on targeting patterns conditionally based on what follows. Use negative lookbehind to skip or red apple. The fruit string contains different apples. Match apples when it is not preceded by red. Print the matches. Running the cell now. Here, the output, apple, apple, shows that the negative lookbehind successfully excluded red apples while still matching apple in other contexts. Notice that both standalone apple and yellow apples contain apple, but only apples not preceded by ready is captured, highlighting how negative lookbehind refines pattern matching without capturing unwanted cases. Use a non-capturing group to match both HTTP and HTTPS URLs. The URL string has two sample URLs. Match HTTP or HTTPS, followed by ;//, then words and dots. Print the found matches. Running the cell now. This output shows a list of URLs matched using a regex with a non-capturing group, HTTPS. Notice that both HTTPS and HTTP URLs are correctly found without saving the protocol part separately. This demonstrates how non-capturing groups cleanly group patterns without cluttering your results with unnecessary submatches. Show the difference between greedy and non-greedy matching. Here is a string with simple HTML tags. Greedy, match as much as possible. Non-greedy, match as little as possible. Print both results. Running the cell now. This output shows how greedy matching captures the longest possible string between IP and IP, combining both tags into one match, while non-greedy matching stops at the first closing tag, producing separate matches. Notice how this distinction helps control pattern scope, which is crucial when extracting precise pieces of HTML or text using regex. Error handling and debugging. Always check if result is not none before using groups. Catch re.error for invalid patterns. Print helpful messages to debug. Running the cell now. Safely extract group values only if a match is found. The user string contains a name. Try a pattern to catch the name. Print username if found. Show an error message otherwise. Running the cell now. The output found user, Alice, confirms that the regex pattern successfully matched and extracted the username from the string. This highlights the importance of checking if match is not none before accessing groups, preventing errors if the pattern doesn't find a match. It demonstrates safe, effective extraction aligned with the lesson's focus on error handling in regex operations. Show what happens with an invalid regex pattern. Try searching with an unclosed bracket. Catch and print the regex error. Running the cell now. This output shows the caught error from using an invalid regex pattern with an unclosed character set. Notice the clear error message unterminated character set at position 0, which helps identify and debug the specific issue. This demonstrates the lesson's point on catching regex exceptions and providing helpful feedback for error handling. Best practices in regex. Use raw strings, prefix R, for patterns. Compile patterns if used often. Write simple, readable patterns. Comment complex regex with inline comments. Test patterns with real data. Running the cell now. Compile an email pattern for reuse. Here are some sentences to test. Check each sentence for matched emails. Print the test sentence. Show a list of emails found in that sentence. Running the cell now. This output shows how compiling a regex pattern once and reusing it efficiently finds all email-like substrings in each input sentence. Notice the pattern correctly captures emails when present, non-empty lists, and returns empty lists when none are found, demonstrating readable, reusable regex that fits our best practice of compiling patterns used multiple times. Add comments inside regex by using the verbose flag. Write a pattern to match year, month, and day. Test string has a date. Search for the date parts. Print year, month, day from the groups if found. Running the cell now. This output shows the extracted year, month, and day from the date string using a readable, well-commented regex pattern compiled with the re-verbose flag. Notice how the inline comments clarify each capture group, making the pattern easier to understand and maintain, which aligns with best practices for writing clean, documented regex. Mini-project, validate emails in a list. Check if emails are valid using regex. Only accept emails with letters, numbers, underscores, dots and must have a @ and domain. Running the cell now. Validate several emails using a compiled regex pattern. A sample list of possible emails. Make a pattern to check proper emails. Go through each email in the list. If the email is valid, show it as valid. If not, show it as invalid. Running the cell now. This output shows which emails from the list match the regex pattern for valid email formats. Notice valid emails like bob@gmail.com have a proper username, and domain with a top-level domain, while invalid ones either lack a proper domain or have multiple symbols. This confirms that the regex correctly filters emails based on the intended formatting rules. Ask the user to type a string and a regex pattern. Get a string from the user. Get a regex pattern from the user. Try to find all matches. Print the matches if it worked. If it failed, print the error. Running the cell now. This output shows that the regex pattern 0 to 9 plus successfully matched the digits of 123 within the input string ABC123. It demonstrates how to test and refine regex patterns interactively, which is crucial for accurately validating parts of an email like numeric sections or domains in the project. Notice how the matches list captures only the numbers, confirming the pattern selectivity. Thanks and next steps. Thank you for learning regex with us. Please subscribe to our YouTube for more tutorials. Try using regex in your Python projects. Running the cell now.